In this presentation, we will be explaining some of the scientific concepts behind figure skating. First, we will begin by talking about what makes ice skating happen. This is friction. Friction is defined as a force that resists when two objects slide against each other, dissipating their energy of motion. The difference between dancing on a floor and skating on ice is the lack of friction. Smooth ice provides very little resistance against objects, like ice skates, being dragged across its surface. Compared to a wooden floor, ice has much less friction. The general low level of friction on ice allows a skater to glide along the surface smoothly without friction stopping the motion as soon as it's begun. Next, we will take a closer look at spinning by discussing angular momentum. Momentum is how much force it would take to stop a moving object. The heavier something is, the faster it's moving, the more momentum it will have, and the harder it will be to slow it down. Angular momentum applies to a body rotating around a fixed object. The amount of angular momentum, say a skater has, depends on both the speed of rotation and the weight and distribution of mass around the center. When a figure skater pulls in her arms when executing a turn, she spins more quickly. With arms outstretched, her mass is distributed over a greater space. When she draws her arms inwards, that distribution is reduced, so her speed must pick up to counteract the difference. Angular momentum equals R times M times V, with R being the distance from mass of rotating axis, M is the mass, and V is velocity. As you can see, the figure skater moves from a larger circle to a smaller circle by bringing her legs and arms closer to her center of mass. This changes the R value for the momentum equation. Momentum is always conserved. If M is constant and L is constant, then if R is less, V will have to be greater and you'll spin faster. If R is more, V will have to be less and you'll spin slower. Next, we will be talking about angular momentum in relation to the moment of inertia. Angular momentum during a spin equals moment of inertia times omega, which is angular velocity. Moment of inertia is how hard or easy it is to rotate. The equation is mass times r squared. The lower r is, the lower I will be. Lower I equals greater angular velocity. R is the distance from center of rotating axis. When the skater brings her arms in, she spins faster because she's changing the R distance, which creates a difference in moment of inertia. This is an example of a skater continuing to change her moment of inertia by changing her body position. R is greater, which means her moment of inertia is greater and her angular velocity is less. R is smaller, which means her moment of inertia is smaller and her angular velocity is larger. This follows with the moment of inertia equation. So by decreasing R, you are ultimately spinning faster, and by increasing R, you are ultimately spinning slower. According to the law of conservation of momentum, the angular momentum before is equal to the momentum after the spin. Putting it all together, this skater has to compensate for her change in moment of inertia by changing her angular velocity since angular momentum is conserved.